Май, привет.
Привет.
Поедешь на покров завтра?
Нет.
Ну, если что, приезжай, это довольно классно, когда нет людей. Всем салам. Салам. Мог бы лично сказать, но... Йоу.
Hello, everyone.
Приветствую.
Hi.
Как-то Марии Судакова не видно, подозрительно.
Sorry, I am here.
Жалкая попытка еще.
Жалкая попытка, я не умею пародировать.
Ну, может, когда-нибудь получится у тебя пародировать женский голос. Хотя... Но у тебя голос вроде не такой низкий, чтобы ты прям не мог никогда.
Давай попытка номер 2.
Мы в тебя верим.
Давай.
Нет, нахер. Нет.
Говори, короче, с
Кринж.
придыханием. Говори, смотри, с придыханием, с ну, таким средненьким английским акцентом, и делай вид, что не понимаешь очевидные вещи.
Дайте я попробую. Дайте я попробую.
Давай.
I see.
Guys.
О, хорош!
Yes. Now I see.
Да-да-да-да.
I just want to
Good evening.
Good evening.
Hello.
Hello. Dear students, okay. Let's begin. Let me claim host first, and then I'll share the whiteboard with you. Where did we stop last time? At which problem? Do you remember? We studied problems from problem set 6, but at which one did we stop? Was anybody present last time?
Yes.
4B.
4B. Okay, this was the last one we solved. Okay.
Why?
Can you see the whiteboard?
Yes.
That's pretty clear.
Okay. So our next problem is as follows. We want to prove that there is no such set R that for every x belongs to R. Please switch off your microphone if you don't want to use it.
Excuse me, I have a question about our colloquium. Will we
Yeah.
have it in December or in January?
Most likely in January.
Okay, thank you.
So, okay, there is no such set R that X belongs to R if and only if X does not belong to X. In fact, we have already considered this problem, but now let's repeat why this set is not possible, and then we will discuss why this fact is important. Can anybody prove that no such set R is possible? That is, if it exists, then one can obtain a contradiction.
Yes.
So please.
Let's notice when for every x can't belong to x because if it's true, we can create an infinitesimal sequence of x belonging to x.
I see. It is not infinitesimal, but it is just infinite.
Yes, infinite. And if we have such R, that for every x belongs to R, then R belongs to R. But it's also impossible for the same reason.
Mhm.
And it's impossible due to axiom of foundation.
So I see. So the main idea is as follows. You want to apply the axiom of foundation. The axiom of foundation forbids X to be an element of itself. So this set must be a set of all sets in existence. But then R must be an element of itself, which is not possible, again, by the same axiom of foundation. Of course, that's true. But in mathematics, it is in general good to prove a statement from weaker assumptions. The weaker assumptions you use, the stronger your statement is. So it is interesting to prove that this set is not possible even if you do not assume the axiom of foundation. So let's prove it without the axiom of foundation. Even without this axiom, this R is still not possible. By the way, this R is paradoxical. It says that X belongs to R, X satisfies this property R if and only if it doesn't belong to itself. So what if we consider R itself, where the R belongs to R? Assume that R exists. So the question is where the R belongs to R. This question is entirely legitimate because this must be a statement, either true or false. But what if R belongs to R? Then what should we obtain then?
A contradiction.
Why?
Then
Because there are
R
two ways.
doesn't belong to R. Then
Of course, you know, this statement is something we are given with. We can just substitute R for X. Why not? This is true for every X, including R itself. So if R belongs to R, then there should be that R doesn't belong to R, which is not possible. So this is not possible. And likewise, if R doesn't belong to R, then this is true, the right-hand side. Hence, R must be an element of R, which is impossible either. Is it clear?
Yes.
So in either case, we have got a contradiction. This one cannot be neither true, can be neither true nor false. This is not possible. So R cannot exist. Is it clear?
Yes.
Of course, this condition is somewhat peculiar. Why do we want to consider such strange condition? In fact, this condition is, of course, special. It is a set theoretic rephrasal of the well-known, say, liar's paradox. This statement is false, or even more, it is even more similar to the well-known barber's paradox. In some village, there was a barber who shaved everyone who didn't shave himself. Did he shave himself, the barber? If he did, then here there should be So he didn't, because he shaved everyone, and just those persons who didn't shave themselves. So something like that. The description of this set is contradictive. And what does it mean? That means, for example, that we can disprove the existence of the set of all sets without the axiom of foundation. The set of all sets is not possible even if sets which are elements of themselves are allowed. So let V be the set of all sets. That is, for every x, x belongs to V. And then by our second set construction principle, there exists a set R prime, where R prime is the set of all x from V, such that x doesn't belong to itself. Is this idea clear?
Yes.
Do you remember the second principle? The second principle guarantees that if A is a set and phi is a predicate, then there exists such a set of all elements from A which satisfy phi. So that means that this set must exist. It must exist on one hand, and on the other hand, it is still paradoxical. It is still paradoxical. Why? Assume that the same question is crucial, whether R prime belongs to R prime. If it does, then by the second principle, by the definition of this set builder, as they say, notation, that means that R prime is not an element of R prime, which is contradictive. Is it clear?
You have R with 2 primes, or it's just
Just one prime. This is the
Okay.
same. And likewise, assume that R prime is not an element of R prime. Okay, we know that this set contains every x which does not belong to itself and belongs to V. But we know that every set belongs to V. Every set. That means that R prime belongs to V as well. Is it clear?
yes.
So again, we have that R prime is an element of R prime, which is contradictive. So this way, if there were the set of all sets, then our second set construction principle, otherwise innocent, it would lead us to a contradiction. Is it clear?
Yes.
So that means that there is no set of all sets independently of this axiom of foundation. Whether you assume it or not, the set of all sets is not possible. By the way, this situation explains why in general in our set construction principle 2, we have insisted on this restriction. We want to take all x's from some given, some pre-existent set A. because without this restriction, it would be possible to form R the following way. Let's take all x's in general, all x's which do not belong to themselves. Then we would obtain a paradoxical set R, and in fact, this very observation was the original historical Russell's paradox. So it is not possible, it is contradictive to bring together all sets with some property. It is not possible to group them together without any additional restrictions. So we can group together only the elements of some pre-existent set. Is this idea clear?
Yes.
Of course, this point is somewhat philosophical, and we'd better move on to more easily comprehensible things, like our problem 6. This problem 6 is about the set of all sets, the power set. The power set exists and is defined indeed by our third set existence principle. Please state this principle. It is about the power set. What can you say about the power set? Can anybody formulate the principle?
For every set, there exists
For
set.
every set, there exists a set which is denoted P of A, such that with
such
some
that
property.
all the combinations from set A.
What do you mean by combinations? This is some foreign
Subset.
notion.
Subset, I guess.
So which property do we want to stipulate about this P of A? Which property?
It includes all subsets from A.
What do I mean by includes? Please be more precise.
Contains. No.
For all x,
It is
x
set
is
of
an element of
subsets.
power set if and only if x is a subset of A.
Yeah, if and only if X is a subset of A. So please repeat as I haven't got what you've said. X is a subset of A if and only if.
X is an element of the power set.
Yeah, X is an element of this power set. It belongs to this set if and only if X is a subset of A. So this is a set of all subsets and nothing else. And our principle says that such a set exists. If you want to prove anything about this P of A, what is the base for your reasoning? The base is always this property. If you want to know anything about P of A, you start with this property. X belongs to P of A if and only if X is a subset of A. By the way, do you agree that every set is a subset of itself?
Yes.
Yes.
What does it mean in terms of P of A? Please translate it into some statement about P of A.
For every A belongs to P of A.
Yeah. By the way, as a corollary, we can notice that for no A, P of A is empty. It is always non-empty. Do you agree?
Yes.
What else do we know about subsets? What if, what can you say about an arbitrary set A and the empty set?
Empty set belongs to A.
Belongs, really?
No.
Really? So
Empty set is a subset.
It's a subset.
is a subset, of course. You know, empty set, at least, it doesn't belong to itself, for it is empty, first of all. But the empty set is a subset of every set. What does it mean? That means that every element of the empty set, of which we have none, of course, every element, every present king of France belongs to whatever set. And in terms of P of A, what does it mean?
It belongs to any power set, like empty set.
Of course, the power set of A always contains the empty set.
Excuse
And
me,
now-
and what is power set of the empty set? Then?
It is quite
Just
an
empty
interesting
set?
question. No, it is not empty. We have just proved that no power set is empty. In fact, it must contain the empty set. Is it clear? So it has at least one element, the
So
empty
it's like
set.
singleton of empty set.
Yeah, and in fact, it has no other element. Let's prove it. Assume that X belongs to this set. What does it mean? That means that X is a subset of the empty set. It is quite easy to prove, should I reproduce the proof, that if something is a subset of the empty set, then it is empty itself. Or is it clear?
Of course, it's clear.
Okay, so now we see that the empty set is a subset of the set, and on the other hand, every element of this set, every element of P of the empty set is empty. Hence, the empty set is only element, so it is a singleton. We see that for each X, X is an element of this set, if and only if X is empty. And on the other hand, by the definition, this is equivalent to this one. So we see that X belongs to P of the empty set if and only if X belongs to the singleton of the empty set. Hence, it is the singleton, it equals the singleton of the empty set. Is it clear?
Yes.
Okay, and now, our next problem you have anticipated, in fact, with this question, is to compute the set, the power set of this set, where we have three distinct numbers, 1, 2, 3. Which subsets do we have here?
3 singletons of 1, 2, 3, then set 1, 2, 2, 3, 1, 3, and
what about the empty set?
the empty
And the
set.
empty set.
Clearly, the empty set is necessary. The empty set is always present in any power set. Likewise, our set itself must present as well. So here we most surely have the empty set and our set itself, and some other sets. In fact, here we have all three singletons. Why are they here? Clearly, this singleton of, say, 1 is a subset of this set. Why? Because its only element, that is 1, belongs to this set. Is it clear?
Yes.
And what else? What else do we have here? Singleton, the empty set, this set
Like
itself.
1, 2, 2, 3, and 1, 3.
Aha, 3 pairs. 3 pairs. Also, we have 3 pairs. And totally, overall, we have how many elements here? How many elements do we have here?
8, I think.
8, of course. They are all pairwise distinct, of course. Neither is empty. This one is not equal to this one, for 3 belongs to this set, but it doesn't belong to this one. This one is, say, distinct from this one as 1 belongs to this one, but not to this one. So they are all distinct. We have 8 of them. That is, 8 is 2 to the power 3. And it is not a coincidence as here that here we have 3 elements. Is this idea clear?
Yes.
We shall see that for a finite set, this power is very similar to the function 2 to the power n. But now let's construct some graphical representation for the same idea. First of all, let us prove that here we have, in fact, no more than these 8 subsets. We can construct a tree of all possible subsets. Okay. Assume that X is a subset of this set. Then there are just 2 mutually exclusive possibilities. Either 1 belongs to X or 1 doesn't belong to X. Do you agree?
Yes.
Yes, of course.
For each of these 2 possibilities, we again have 2 possibilities. Either 2 belongs to X or it doesn't belong. Do you agree?
Yes.
Yes. And for each of these 4 possibilities, we have 2 more. Either what?
3 belongs
3
to
belongs
X,
to
doesn't.
X or not.
Sure. And here, what if all the 3 elements belong to X? What's X? Given X is a subset of 1, 2, 3.
Itself, 1, 2, 3.
Surely. What if we have 1 and 2, but not 3?
1 and 2.
The pair 1, 2. What if we have 1, but not 2, while 3 belongs? 1, 3.
1 and 3.
Here, this branch.
Just 1.
The singleton of 1. And here, what do we have? 1, no 1, but 2 and 3.
2, 3.
Here.
Empty set.
Really?
But
2 belongs to X.
sorry, I just was watching another thing. Yeah.
This
then 2.
singleton of 2.
I
And
was watching
here,
another branch.
I see. Here,
3.
the singleton of 3, not 3 itself, of course. And what if neither element belongs to X?
Then this set is empty.
And now, another interesting idea is to construct a graph representing which subset is included into which one. So, do you know how it is possible to draw a cube?
Yes.
Have you ever drawn a cube?
Yes.
So, a cube, or more formally, its planar projection is somewhat like this. Do you agree?
Yeah.
And now let's mark the vertices of this cube by with our subsets. So let's mark this one with the empty set, and now its neighbors will be the sets which disagree with the empty set in just one element. They are singletons, so the only difference between this one and this one is one. One belongs to this set, but not to this one. So here we have something like that. Do you agree?
Yes.
And now here I want to place a set which disagrees with both singletons in just one element. What is it?
Set of 1 and 2.
And here?
Set of 2 and 3.
Here?
Set of 1 and 3.
No.
Oh, 1, 2, 3.
And here in this back vertex,
1
we
and
will
3.
have 1 and 3. By the way, you can make arrows from these edges, and these arrows then will coincide with set inclusion. Is it clear?
Yes.
So here every subset is connected to all subsets which disagree with it in exactly one element. As potentially we have 3 elements, then every subset has exactly 3 neighbors. So we have a kind of a graph. We will study graphs in much more detail later, and also we will come back to this so-called Boolean cube or cubic graph. This is a very important kind of a graph. Is this idea clear?
Yes, but when we will study graphs? Like
Most likely in February.
I understand.
Okay. Now let us prove something more formal. For every 2 sets x and y, P of x is a subset of P of y if and only if x is a subset of y. Can you prove it? Here we have 2 implications. This theorem says that this statement holds if and only if this one does. So here we have 2 implications to prove. The first one is as follows. Assume that it is given that P of x is a subset of P of y. That means that every subset of x is also a subset of y, and it is required to prove that x itself is a subset of y. Please produce the most concise proof you can.
Well, actually, well, let's just remember the definition of this subset, this function of all subsets of x. I suggest.
It is a set of all subsets.
Yes, of x.
Of course. So we can access it using this statement. This is, say, the definition.
Yes, so we just maybe should consider, yes, these 2.
So you know that every subset of X is a subset of Y, but why X itself is a subset of Y? It's very easy.
In
Because
the power set of
yeah,
X, there exists set X itself.
yes,
And if it contains in the
Aha! X is a subset of X.
and X.
Have I got you right? Then X is is an element of P of X.
yes, and
Yes.
it is an element of P of Y.
Sure, because yes, because of the assumption, then X is an element of P of Y, which means by the definition of P that X is a subset of Y. That's all. Is it clear?
Yes.
Please notice that here we haven't considered the elements of X. Of course, it is what was possible to prove it by definition of set inclusion. Assume that A is an element of X. Then we have to construct some subset that contains A. By the way, it's all the same in general. But these steps considering the elements of X, they are in fact unnecessary. And now, for the other direction, it is given that X is a subset of Y, and it is required to prove that P of X is a subset of P of Y.
Can we say that X is a subset of P of Y?
In general, we can't. Why? Why should it be so? We know that X is a subset of Y and Y is an element of P of Y, but this does not imply that X is an element or a subset of P of Y.
Let's see.
This gives us nothing. So our best chance is to start with the definition. Assume that some A indeed belongs to P of X. What does it mean? That means that A is
Subset of X.
Yeah, that is A is a subset of X. And what can we conclude in view of this assumption?
Power set of A is subset of power set of X, maybe.
This is required. No, it is too early for this conclusion. You know, A is a subset of X. X is a subset of Y. And what of it?
A is a subset of Y.
Of course, because being a subset is a transitive relation. A subset of my subset is my subset, but it is not this. It is not so for elementhood. An element of my element can be not my element. But for subsets, we have transitivity, as we have already proved. Is it clear?
Yes.
But this means that A is an element of P of Y. So every A, be it an element of P of X, it must be an element of P of Y. And this is true for every A. This is true for every A. That is, every A from P of X is an element of P of Y. That is, P of X is a subset of P of Y, which was to be proved. Is this idea clear?
Yes.
Yeah.
I hope it is quite logical. By the way, dear students, you should use logic, our axioms, our principles. Most of you want to apply some intuition. Say, the intuition rigidly connected to these diagrams. But diagrams are imperfect. They are one-dimensional in a sense. It is not possible to plausibly depict the power set of some set or something else. So many set theoretic constructions are out of the reach of these diagrams. So please use logic. You will develop some good intuition, but not immediately. Just after you have obtained some experience with logical arguments. Okay. And now let's let's recall our identities. Do you remember the identities like that? A intersection B equals B intersection A. Do you remember this?
Yes.
In fact, we have had a special theorem under the name set algebra identities. We had quite a long list of identities. You'd better memorize. And now let's prove some of them. Okay, as an exercise, let's consider this one. What if I take A union B intersection C? What can you say about this set? What is it?
It is A union B, intersection C.
Intersection and A union C.
Intersection A union C. This way.
Yes.
I think so.
Mm-hmm. But how is it possible to prove it? We will apply the most general procedure. We will prove that every x belongs to the left-hand side if and only if it belongs to the right-hand side. Okay. Consider an arbitrary x and let us say, what does it mean that x belongs to the left-hand side? What does it mean? X belongs to the union.
It either belongs to A or it belongs to B and C.
Yeah. By the
section.
first set construction principle, we know that X belongs to the union if and only if it either belongs to the first set or to the second one, which is an intersection in this case. Mm-hmm. What's next?
Or X belongs to B and X belongs to C.
Aha, so here we have a disjunction of two statements, of which the second one is a conjunction. What should we do with this composite compound statement?
Split it, I don't know.
Split, what do you mean by splitting it?
No
Like
clue.
indicatable.
Aha, we want to somehow transform it. But you need a table for which statement? If it is alpha, this one is beta, and this one is gamma. Please notice that all three are statements for fixed x, a, b, and c. We have the following. This statement is logically equivalent to which one?
Alpha or beta and alpha or gamma.
Aha! But what does it mean that two compound statements are logically equivalent? That means that their
Have the same value.
truth tables are the same. Yeah. Do you agree?
Yes.
Yes.
Okay, and now let us construct the truth table and check it immediately. So this is say phi, and this is say psi. How many rows will this truth table have?
20 power of
8.
3.
Yeah, 8 rows. 0, 0, 0, all possible ways to give some truth values for A, B, and alpha, beta, and gamma. 0, 1, 1. What else? What's next?
All ones.
1, 0, 0,
1, 1, 0.
1, 1, 0, and 1, 1, 1. Mhm. Okay, let us see. What if alpha is true? What can you say about the first disjunction?
And it's true.
It must be true, of course. And what if alpha is false? When alpha is false, the value of this disjunction is the same as the value of its second term of this conjunction. Do you agree?
Yes.
So here we will have 0, 0, 0, and 1. This is for phi. Do you agree?
Yes.
And what would we have for psi?
If alpha is 1, so it's also true.
Yes, if alpha takes value 1, then both these disjunctions are true and the conjunction is true as well. So in this part of the table, we see no difference between phi and psi. And what if alpha is false?
And if beta and gamma are 1s, so the psi is true. In the other cases, of course, it's all false.
So we see that these truth tables do coincide. They're the same, that is irrespective of the nature of alpha, beta, and gamma, these two statements are always equivalent. They take the same value. That means that here, X and A, or X and B, and these two, they take the same value. Do you agree?
Yes.
What's next? What does it mean that X belongs to A or X belongs to B?
A union B.
Not, of course, A union B, but X belongs to X
Oh,
union
yes.
B. It is a statement, while A union B is not a statement. It is a set. A set is something. It is what? And a statement is something which is either true or false. Is this idea clear? It is not an entity.
Yes.
It is a property. And here we have some problems here on my side. So then we have this one, which means that X belongs to what? To the intersection of these two, isn't it?
Yes, it is.
Which is exactly our right-hand side. Thus, we have proved our identity. And in fact, one can prove any identity of this form, given it is true, this way. Is it clear?
Yes.
But now, our next goal is to apply these identities to from our theorem, I mean, to get more identities. first of all, let us prove that for whatever sets A, B, and C, A minus B union C equals A minus B minus C. First of all, by the way, what is the difference of two sets? What is X minus Y?
This is when
It's
it's
every element
X.
that
It is a set of all such elements where from?
that belongs to A, but not X,
What,
but not belongs to Y.
Yeah. So you take all elements from X which do not belong to Y. Is it clear?
Yes.
But what should we do here? Of course, we can use this statement and then analyze it element-wise. But there is a better way, much better way. We can somehow apply the identities we already know. But how? Our identities, by the way, didn't mention difference, but rather they mentioned what? The
intersection, but they can
union.
Not intersection, not union. What else?
Negation.
Negation. But this is called the complement. It is negation for statements, but a similar operation for sets is called complement. But what is a complement? Complement is a unary operation. What is the complement? What is the complement of the set X? It is
everything
a set
which lies beyond X.
Aha! But what do you mean by beyond?
Every element which
belongs to
doesn't
what?
belong.
To what? Belongs
Depends
to something, but not X. Aha! So this operation is relative to some fixed set, which is usually called the universe. So it is not possible to say about complement in some absolute sense. You only have complements to some universe. So if we have fixed some U, which includes X, then you can define the complement to this U. Is it clear?
Yes.
Yes.
And if X and Y are both subsets of this universe U, then it is possible to get rid of set difference and rewrite it in terms of the complement. So please.
Maybe X intersection complement Y.
Of course, this is a set of all elements which belong to X, but they do not belong to Y. That is, they belong to U minus Y. Is this idea clear?
Yes.
Yes.
Let me even make a diagram. This transformation is routine, but here we still have some problem. How is it possible to take U? How is it possible to take U? So the difference is here. The difference is here. And what is the complement of Y? The complement of Y, or the complement to Y is this greenish area. Do you agree?
Yes.
And we're interested in its intersection with X. Green plus blue result in red. Of course, it is strange from physical point of view, but okay. This is a illustration for this identity, while of course it is not necessary to prove it. Returning to our problem, here we want to apply this equation, but in order to do so, we need some universe. What can one take as a universe in this problem?
Set A.
Field of real numbers. for
Set
example.
A, really, but will B be a subset of A? Not necessarily so.
Maybe
But the
union of A, B.
A, B, and
Of
C.
course. The routine approach is to take just the union of all these three sets. Then clearly, all the three sets will be subsets. If they are subsets, then we can rewrite our left-hand side the following way. The left-hand side equals A minus this union, that is, so please rewrite it.
A intersection B union C
The
negation.
complement,
Your complement, sorry. Yeah.
What's next? What should we apply? Do you,
Identities.
what?
Sorry.
Do
I
you,
just-
do
The
you
more
know,
the
do you
more.
know, of course, some identity.
I want to say yes.
Exactly one of De Morgan's laws. So we know that the complement to union is
Complement of B, intersection, complement of
the intersection of complements. What's next? Please remember that our right-hand side is just that.
And then A in union with B negation.
Union, really.
No, intersection.
Intersection, we can regroup it. We can regroup it using associativity law. And then
And then
this one is A minus B.
yeah.
and minus C.
Which is exactly our right-hand side. Please notice that the universe and the complement, they are omitted from the left-hand side and the right-hand side. So universe was necessary to prove it. No, not necessary, of course. It was used to prove it, but there is no universe in the statement of this theorem. Is it clear?
Yes.
Yes.
And now let us prove something else with our identities. The next theorem is somewhat obvious, and it can be easily proved using elements, but we don't want to consider particular elements of our sets. Let's use identities. First of all, let's recall how is it possible to replace set inclusion by an identity. X is included to Y when what equals what?
All elements.
When A union B.
A really, X and Y.
Sorry.
Well, all elements of
S.
X.
X union Y equals Y.
Of course, all elements of X belong to Y, but we're interested in some identity. So please, X union Y equals
Y.
And what else with intersection? Do we have a version with intersection?
Yes, X intersection Y equals X.
These are very important. Okay. And now let's try to prove it using these facts. First of all, from the right to the left, that's trivial. You know, A union B equals what? Assume that it is given that A equals B. Then A union B equals what?
A or B.
Yes, it is A union A, which is just A. Do you agree?
Yes.
But of course, it is also A intersection A.
Which is
And-
A intersection B.
Yeah, I can replace A by B one more time. So that's easier. Is it clear?
Yeah.
And now we have a somewhat more complicated problem. Assume that this intersection equals the union. And now we are required to prove that A equals B. But A equals B is, by the way, equivalent to two inclusions. Do you agree?
Yes.
What should I do? I don't want to consider elements.
That is
We
like
can write equivalent like in the previous one of the previous examples, like A union brackets A
Aha! We know quite well
Yeah.
that these two sets are equal.
exactly.
This is known as an absorption law. We have two absorption laws. Aha, A equals this thing. Interesting. But clearly, this part can be replaced. This term is replaceable by the union. Do you agree?
Yes.
Yes.
What's next?
We can open
Then
these
that
brackets.
will be equal to A.
Union
Not
B.
A.
No,
Yeah,
I
yeah.
know, I just
Uh,
A union A.
we see
union
that
B.
it is A union B. A union B. Interesting. But here it is possible to say replace it one more time. We can replace it one more time. We can change it to A intersection
Actually,
B.
there is no need to do it again because they are already proved that A is equal to A union B. So like similar, they can prove that B
No,
is equal
why do
A
we know
union B.
that A equals A union B?
According to
I
our
see.
definition.
A equals A union B.
Yeah, and just the same operations, we can prove that B is equal to.
I see. You want to conclude that B is a subset of A from this one. Of course, I see your point. But there is a more elegant way to do this in a chain of equalities. So what if we do something like that? What if we consider it this way? Is it possible?
Yes, we can.
Yes.
And then we regroup. It is symmetric to the first part of this chain. Then we regroup. Then we change. A intersection B by the union one more time. And then we will apply the respective absorption law and obtain B. Is it clear?
Yes.
You know, the absorption laws are as follows. We have two of them. The union of X and the intersection equals X. And the intersection of X and X union Y equals X as well. By the way, these laws are similar to those we have for numbers. Say the least common multiple of X and the greatest common divisor of X and Y is what? What is the least common multiple? Yeah, it is X. It is X because this number must be divisible by X and it must divide so it is X. It is not hard to prove it. But anyway, we have some questions, so please.
I know that might be strange, not the best question, but I just, yes, about the absorption rules. They both equal to X, but can we say that they equal to to each other?
Of course, they are.
Okay.
If they both equal X, then they equal to each other. Surely. Okay. And one more. So please still we want to avoid considering particular elements. Assume that A is a subset of B and A is a subset of C. Then A is a subset of what?
B intersection.
B union C.
Not only
intersection, yeah.
union, but intersection. In fact, these two are equivalent. Okay, let's prove it. First of all, we want to, most likely, we want to replace this inclusion by an identity. Which identity should we take?
That any element of A
No
is-
elements, no elements. We want an identity. Some set equals another one.
A is a B without
A
A is a B without A
really
с крышкой.
с
Like
крышкой.
negation to A.
The complement, but
Yes.
aha. So A is what?
B without accomplishment or accomplishment to A.
Complement.
Complement.
From the word complete. Complement. You complete it, so you obtain a complement. So A equals B without the complement, but the complement to which set? That's strange. That's strange, but if we have some universe, then this is just B intersection the complement to the complement, that is B intersection A. So it is way better to state it without any mentioning of complements. Do you remember this fact? X is a subset of Y if and only if the intersection equals the lesser set.
Yes.
So we have this one. And likewise here, we have that A equals A intersection C. While this is equivalent to which statement? A equals?
A intersection B. C.
This one. Is it clear?
Yes.
So now our goal is to prove the third one from the first one and from the second one, and vice versa. Okay, assume that the first and the second are given. Then what do we have? Then A equals what?
A intersection B, and then we can just substitute A intersection C.
Of course, we can replace this copy of A by A intersection C. But of course, this is not optimal way. But anyway, what's next?
Just
Second
change
of
the
all.
brackets.
Regroup. First, regroup. What's next? It is not the same. Graphically, I mean. We have two distinct terms. What's
Why
next?
it is not the same?
They are equal, but the term itself, the expression is different.
Yeah, because commutative.
The order of B and C.
Then we must swap B and C. We have to apply commutativity. And now they are clearly the same. Is it clear? Of course, we can spare some effort if we start from the second one, not from the first one. So 3 follows from 1 and 2, and vice versa. Assume that it is given that A equals this set, and I am required to prove both this one and this one. How is it possible to do so?
You can do it just in reverse order. Like open the brackets.
Open the brackets here. Where? This is given.
Yes, exactly.
And what
There.
out of it? That's given. What's next?
Never mind.
Regroup it.
Regroup. Okay, I see that A equals A intersection B intersection C, and what of it?
Why can't we use the definition maybe or something?
We can use the definition, but we don't want. We try to think like algebraist. We want to develop some method of proving things using identities. Of course, we can always resort to the definition. The definition is our best friend, but nevertheless, sometimes there are more elegant ways. You know, if two sets are equal, then of course their intersections with whatever sets are the same. Do you agree?
Yes.
And
Yes.
then we can transform this part. We use associativity and commutativity. C intersection C. And what is C intersection C?
Itself.
It is C for idempotence, of course. So here we have this thing, which is almost, not almost, but exactly A, by the same star-marked identity. Is it clear?
Yes.
We use it 2 times. So
So-
we have obtained this one.
But in this case, we can see that A intersection C is equal to A. And,
Yes.
and then A intersection B is equal to A. And
No, this is for the second
but
one.
it is
And
A.
now this is for the second one. A intersection C equals A, hence A is a subset of C. And if you want the first one, you should, of course, intersect both sides, not by C, but by B. You should intersect both sides by B, and then open the brackets here. First, you regroup. Then apply commutativity. Then regroup once more. Then apply idempotence. So you have this right-hand side, A intersection B intersection C. So here we have just A, whence A intersection B equals A. So I have obtained this statement. Is it clear?
Yeah.
Here in this proof, I have used nothing else than identities and the fact that equal sets behave identically. So I can freely replace any set by any set equal to it. Say A intersection C equals this right-hand side intersection C, given A equals this thing. Is this idea clear?
Yes.
Do you have any questions?
No.
Dear students, please have some practice with these identities. It is very interesting, in fact. And as an exercise, I would give you the following one. It is out of the scope of our homework, but it is interesting by itself. Assume that the following identities are given. Two absorption laws, but these laws are for whatever X and Y. This is given, and you are required to prove that for every X, X intersection X equals X. Please notice that no other identity, I mean a non-trivial one, of course, X equals X and something like that. No other identity is given. Just these absorption laws. Just these absorption laws and nothing else. So your task here is to try to prove this idempotence law just from this absorption laws and nothing else. Try to prove it using identity manipulations, nothing else. So the main trick here is to guess which X and Y do you need here. That's possible. And the proof is just a one-liner, a one-line proof. But can you devise one? Think about it. If you prove it, you can show me your solution in Telegram if you wish, or you can discuss it among yourselves. Okay.
Do we know in this exercise that X union X is X or not?
Of course not. Of course not. We know nothing else. So you can even replace these two operations by some other operations, say something like that, for whatever it means. Here we have some arbitrary operations which satisfy these identities and nothing else. This is an algebraic exercise. So this is about manipulating identities. Think about it. If you have found a proof, you will be satisfied with it. It is very elegant.
Actually, can we just only need to identity use, or we can use some kind of axioms or?
No, nothing else. These two with general facts about identity, about equality. That is, if X equals, say, Y, then they behave identically. So you can replace identical terms. You can replace equal terms. This is the only thing which is given. The properties of equality and these two identities. Think about it.
And we need to prove that X union
Thank you.
Uh,
Goodbye.
intersection.
Or intersection. So this operation is idempotent. This one, and of course, dually. Here we have symmetry between these two operations, and of course, here there should be symmetry as well. Both hold, but start with one of them. Try to prove it. That's interesting. Do you have any questions?
Yes, can you please share the whiteboard?
Aha, the whiteboard, of course. Tomorrow we will have a lecture. We will consider ordered pairs, Cartesian product of two sets, and hopefully binary relations. We shall start binary relations. So we want to use set theory for formalizing something interesting, some regular mathematics, like say coordinates. We will develop a set theoretic framework for coordinates, like in plane or elsewhere. Have you received the whiteboard?
Yes, thank you.
So thank you, dear students.
Thank you.
ladies and gentlemen.
Goodbye.
Thank you. See
Bye.
you. Bye.
Goodbye. Goodbye.
Yeah, by the way, do you have the whiteboards from lectures?
Yes, I have. I can send it now, but please tell me when did we have our lecture, the date and time.
Oh, okay, I'll contact you on Telegram then.
No,
Okay.
can't you do it immediately? Just
okay.
look at the calendar. So this was November 27, the 27th of November, and about 2 hours, the 27th of November. So probably here it is. I've sent you something. Please check whether it is the lecture's whiteboard. Is it the correct file?
Yeah, it's the correct file. Yes. Thank you.
Okay, thank you. Thank you. So goodbye.
Thank you. Goodbye.
Thank you for the lesson. Bye.
Thank you, dear students. Goodbye.
Thank you. Goodbye.
Goodbye.